In this video, we're going to discuss simple linear regression. And so, usually, a regression analysis follows from a strong linear correlation analysis. So, after we verify that two quantitative variables have a significant, strong linear correlation, we can determine the line of best fit or the equation that best models that data um, in what we call a regression analysis. And so that line of best fit or that line that best models the data is what we're calling our regression line. We saw in our last lecture video that we had a strong, significant linear correlation, and it was positive, between the variables community service hours and happiness score. And so what we can do is now run an analysis so that we can see what is the line of best fit or what line best models that data. And so that brings us to equations of lines. You may remember from algebra learning the equation y equals mx plus b. That is the exact same equation that we're going to use, but of course, this is statistics, so we're going to change some things up because we're going to expand that line to include more x variables. And so when we look at regression equations, especially in the world of simple linear regression, this is what our regression equation looks like. All right. We have a y with a single quote there. You can call that y prime, but it basically represents your predicted values of y for a given x, and that equals a plus b times x. So this looks kind of similar, the order from your normal regression equation, sorry, your normal line. This is your slope-intercept form of an equation of your line in algebra. We just switched some orders here and used a instead of the b here, and we both put a b where this x is. I know it can get confusing. But here we have y prime equals a plus bx. This number that stands outside, or this a here, is going to be replaced by a number that stands out by itself. And this b is also going to be replaced by a number, and it's going to be multiplied by your x. All right, that value b is going to be your slope. So whatever the slope of that line is going to be multiplied by x in the same way that m is in your regular equation of a line. It's a measure of the change in y when x increases by 1 unit. So it tells you how much y is going to either increase or decrease for a 1 unit increase in x. This value a is going to be your y-intercept, right? So your y-intercept is the point where your line actually intersects your y-axis. So it's the value of y when x equals 0. Well, we can find a and b that best fit our data using what we call the least squares regression method, all right? And we're going to talk about that in the next slide. But the least squares regression method allows us to use a formula in order to help us get the value of our y-intercept a and the value of our slope b. These are the values of your slope and your y-intercept. Your slope is given by your sample correlation coefficient times, and I'm going to make a slight correction to match your textbook so that we won't be so confusing here. But our slope is given by this sample correlation coefficient times the ratio of the standard deviation for your y variable divided by the standard deviation of your x variable. That is the formula for your slope. So if you know those three things, you can find your slope in a closed formula, which is very nice. The y-intercept is, once you find your slope, you can find your y-intercept by using this formula here. Y bar is the sample mean of the y variable in your ordered pairs minus your slope times the sample mean of your x variable, right? Now, we can use these formulas to help us get our slope and our y-intercept. However, we're going to use the computer to allow us to do this. And your computer is going to use the least squares criterion or the least squares method for determining your line of best fit. But just remember that this is our equation here, And then we want to be able to remember that A is our y-intercept and B is our slope. And this is what they represent. Before we get to explaining what least squares does for us, I want to talk about something that the least squares method uses, and it's residuals. And so as we take more and more statistics, residuals are going to be very, 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 very important. And so let's define what a residual is. A residual is the difference between an observed value of y, your predicted variable, and a predicted value, right? So this is the formula. It's y minus y prime, or y sub I, because there are going to be multiple individuals or multiple y values in our data set. And so for each ordered pair or each individual in our data set, they have their own residual. That's why I have the subscript I here. And so all we have to do is take the observed y value that's in our data set and subtract from it the predicted y value that's on our line of best fit, that's on our regression line. And so let's talk about what a residual looks like kind of graphically so that we can kind of better understand why we're getting a line of best fit. I'm going to select one ordered pair in our data set, right? So this is an example of an ordered pair, X and Y. And so since we have multiple ordered pairs, I'm calling this X sub 1, comma, Y sub 1. This is the first ordered pair that I'm looking at right now. Well, for every ordered pair, there's a corresponding ordered pair for a point with the same X value, but on our regression line, right? So if I were to go to that point and identify by vertical axis or vertical distance to that line, the corresponding point on that line, I could find out what my predicted Y value is for that same exact X value, right? And I can just look at this point right here, right? So I'm going to point here. That vertical distance there gets me to this point on this line. This point is my predicted Y value for that same X coordinate, right? So now I have a Y sub 1 and a Y prime sub 1. So I have an observed Y value and a predicted Y value. So now I know that they're not the same. So I have a residual that basically represents this vertical distance between my observed point and my predicted point that's on my regression line. So this is my residual Y1 minus Y prime 1. And every single point has a residual like that, right? I can go to another point. I selected a point that's under my regression line here. I'm calling it X sub 2, comma, Y sub 2, because it's not the same points here. So I use a different subscript. And I can find the corresponding point on my regression line to get the predicted value, Y prime sub 2, that corresponds to that same, that other Y value, Y sub 2, right? So I have my vertical line here. There's my point, X sub 2, same X value, but I have the predicted value because I'm on my regression line. And so my residual here still represents that vertical distance, but this time it's going to be negative, right? Because if I do Y sub 2 minus Y prime sub 2, Y prime sub 2 is larger, so I'm going to get a negative value. And my residual here is going to be positive, right? Because the observed value is larger than my predicted value. Because we have points on either side, we're going to have some residuals that are positive and some residuals that are negative. But we want to pay attention to the size of the residuals because the residuals really provide us with a measure of how well the regression line fits our data, right? And it's because the smaller the residual, the better the fit, right? So when we're trying to figure out what's the line of best fit, we got to kind of try to figure out which line would minimize those vertical distances there. That is the least squares method or the least squares criterion. And so the least squares criterion finds the regression line that minimizes the sum of the squared residuals. Now, when we talked about standard deviations, we talked about squaring deviations, because if we add them all up, we're going to end up with 0. The same thing is going to happen here. I pointed out that this residual here is going to be positive because y bar 1 is going to be larger than y prime 1. Sorry, not y bar. Y sub 1 is going to be larger than y prime sub 1, right? But in this case, this residual is going to be negative. And so if I were just to add up all of the residuals together, I'm going to end up with 0 because we're going to have positive and negative values. So when we look at the least squares criterion, we're minimizing the sum of the squared residuals. So I'm going to go to each residual, square them, add them all up, and we're going to pick the line where that value, that sum, is a minimum. This is going to ensure that we get the line of best fit. It actually reduces our overall prediction error. Notice here I'm using the word error here instead of the word residuals. In statistics, a lot of times residuals are replaced with the word errors, or they're synonyms with one another. All right. But that is what your computer is doing when it's creating or finding your line of best fit. Your computer is going to try a bunch of lines with different slopes and y-intercepts, and it's going to land on the line with the slope and the y-intercept that minimizes this sum here, the sum of squared residuals. And it just so happens that it aligns with those formulas for A and B that I gave in that last slide. All right, so let's go back to that last example where we were looking at the amount of community service hours served, and the happiness score. I want to find the regression equation for that example. If you remember, X was the community service hours and Y was our happiness score, right? In JASP, we're going to use the regression menu. We're going to put our predictors in the covariate box, and we're going to put our criterion variable, or what we're predicting, in the dependent variable box. Let's see how we can do that in JASP. All right. This is my data. I kind of already had it loaded here. We're going to use this community service hours 1 and happiness score 1, right? I'm going to go here to the regression menu, and instead of going to correlation like we did for the correlation coefficient, I'm going to go to linear regression here. All right. I said that my dependent variable was our happiness score. That's our Y, so it's going to go in that box there. And then our X variable is going to go in the box for covariates. What I want you to do, so that we get just one output, is I want you to select backward for the method. We're going to revisit this when we extend our analysis to multiple regression, but for now, just choose method equals backward. All right. When you do that, I have multiple tables here. My regression analysis is in this last table with the heading coefficients. All right. With the heading coefficients. And so I'm going to go back to my notes so that we can talk about some of this output here. All right. We want the regression equation, y prime equals a plus bx. In this coefficients table, we have a model which represents our regression equation. This first line gives us information about the intercept. All right, it has intercept. And on the line that corresponds to our X variable, which was community service hours 1 in that data set, this gives us information about the slope. So in this example, I'm going to go to this unstandardized column here. We're not going to worry about standardized here. We'll talk about that when we get to multiple regression. But this is the value of my intercept A, and this is the value of my slope B here. All right. And so my slope is 0.919. Remember, your slope represents the change in y for a 1 unit change in x. My x here is community service hours, right? So I can say for each additional hour of community service completed, my y, or the happiness score, is expected to increase by 0.919 points, um, or units, on average. And I just rounded this 0.919 to zero point 0.9 when I gave that interpretation. All right. My y-intercept is 3.907. Remember, we said that the y-intercept is the value of y when x equals 0. All right. That aligns with the point where your line crosses your x-axis. Well, x equaling 0, meaning a student not completing any community service hours, right? So it says students who complete 0 hours of community service tend to score about 3.9 points on the happiness scale, or whatever battery or assessment that's used to measure happiness. I just called it happiness scale here. But that's 3.9. I rounded that to 3.9. So that is our slope and our y-intercept. And there's an interpretation of both of those. We can put those together into our regression equation, and we get the following regression equation. Y prime equals 3.907 plus 0.919 times x. A lot of times, instead of using x and y, we may use the words that x and y represent in our regression equation. So we can also write it in this form here. Happiness score equals 3.907 plus 0.919 community service hours plus 3 point. We already have the 3.907, so I don't need that extra 3.907 there. Sorry about that. We can write it that way there. So the happiness score equals 3.907 plus 0.919 times community service hours. Now, that's coming from this unstandardized column. There's a standard error. Standard error, remember, that's the standard deviation of your sampling distribution. We have a test statistic. It is a t, which means we're using students' t distribution. And then we have a p-value here. We have a p-value. We must have a hypothesis test. All right, that is the case. Our hypothesis test is the hypothesis test for the slope. Our null hypothesis is that the slope equals 0. Our alternative is usually two-sided here, and that's the test that our slope does not equal 0. And so when I look at those JASP results here for the slope, this is the p-value that corresponds to that. Now, a lot of times in social science research, I'll be honest with you, we're not usually interested in the intercept. We're usually interested in finding significant predictors of the output variable, whether, or a significant relationship. And so we usually don't focus on this in this p-value and a hypothesis test for that intercept, but your statistical software still gives you that information. For us, since we do a lot of social science research, we're going to be focusing on the hypothesis test for the actual slopes. And so based off of the results from JASP, we can say that we would reject the null hypothesis here, that the slope equals 0, and say that we do have enough evidence to conclude that the slope is significantly different from 0 in the population. And all that means is that community service hours is a significant predictor of happiness score. All right? And so we'll look at that to determine if something is a significant predictor or what have you. What we want to do next is to actually use that regression equation to make some predictions. And I want to introduce a term that's going to be very important. And I don't have it written on the screen here. I'm just realizing that. Whenever we want to use our regression equations to make predictions, we have to be careful not to extrapolate. Extrapolate. Extrapolate means to predict your y variable for x values that are beyond the x values that are used to create your regression equation. So, for instance, I know that this is not from my original data set. My original data set, for instance, I'm going to go back to my original data set. My original data set is here. Um, I'm going to change what I have on the in the PowerPoint slide very quickly, right? But if I want to look at this regression equation here that we created, and I talked about extrapolation, I'm going to look at what my minimum value is, and it's probably easier to go back to my results. I'm going to go here to my results. I'm going to do some. Can I add descriptives? I'm going to add descriptives here. And they don't give me the descriptors that I need. So I'm going to add the descriptives here. All right. The reason why I'm doing that is because I want to see what the min and the max are for my community service hours example here. My minimum community service hours is 1.5 and my maximum is 18.6. And I use this data set here to give me my regression results, right? These are my regression results. That was my 0.919, 3.907. The slope and the y-intercept for my data. So what I want to do whenever I make predictions using my regression equation is I want to stick to using values that are in the range or close to the range of values of the data that I originally created my regression equation with. Okay, so I wouldn't want to predict the happiness score for a child that completed 50 hours of community service because my descriptives, my minimum value was 1.5 hours and my maximum was 18.6. So 50 hours is well beyond the range of values that was used to create this regression equation. All right. So what I'm going to do is I'm just going to pick one of these community service hours here. Let's say 13.2. And I'm going to do this in real time instead of using the notes, what I have in the notes here. So 13.2 is here. Notice 13.2, if a student completed 13.2 hours, then their happiness score was 18.2, right? So what I'm going to do in my notes here is I'm going to predict the happiness score using my regression equation for a student who completes 13.2 hours. What I did originally was use this incorrect data set here. So I'm going to remove that. So what that means is I'm going to go back to my regression equation that I just created, and I'm going to replace my x with 13.2, and then I'm going to get my calculator, and I'm going to do that calculation there. So we had 0.919 times 13.2 plus 3.907. That is equal to 16.0378. I'm going to do that one more time in my calculator to make sure that I did not make a mistake. And that is the value that I get, right? So this means that a student who spends 13.2 hours completing community service, they have a score of 16.04. If I round that to the nearest, I'll just round it to the nearest tenth place. We have a score of 16 on the happiness scale. All right, that's the predicted value using our regression equation. Now, this predicted value is not equal to my actual value. I'm going to go back to my data set. 13.2, they corresponded to a happiness score of 18.2. So I can create a residual. We had 18.2 minus the 16. I'm going to use the 16. Let's just go ahead and use the actual value. If I do that calculation, my residual is 2.1622. Okay? So this prediction is 2.1622 units lower than the actual value that I observed in my data set. That's based off of this calculation here. All right. So I'm sorry about that. I had the wrong data set that I was comparing. In my original data set, um, my original plan was to use that data set with just 10 observations. That data set um, was changed, so I used a larger data set so that we can get more practice here. All right, but that is how you can do prediction, and you don't want to extrapolate. Now, I didn't have to use 13.2 hours. I could have used 13, but I chose 13.2 because that was an X value that was in my data set. In real life, I would probably sorry. In real life, I would probably just predict the happiness score for a student who completes 13 hours of community service. But I would never go beyond those values of my X variable that were used in the creation of the actual regression line. If I do that, that is called extrapolation. And the reason why we don't want to extrapolate, so the reason why we don't want to go beyond values between 1.5 and 18.6 is because we are unsure if that same linear pattern that we see in our data here will extend well beyond that, right? After a while, there may be a plateau, right, in the happiness score because there's a maximum of 20 points, right? So after a person, maybe gets to 20 or 25 hours of community service, maybe all of those individuals are going to be very similarly happy. And if we were to use the regression equation that's used for the individuals from 1.5 to 18.6, we may be erroneously making predictions beyond what we would have. And so that was a long way. That took me a long roundabout way to get there. But use the values that are similar to the values that are in your data set, the X values in the range of the um, ones used in your data set whenever you're making predictions. You can go slightly beyond that. So it would be okay to do about 20. But if you go far beyond that, you're not going to be able to believe the predictions that are made. All right. All right. So next, what we want to do is we want to talk about whether our obtained regression model is a good model or not. And that leads us to what we call the coefficient of determination. The coefficient of determination represents the proportion of variance in your y variable that is explained by or accounted for by the predictor variable x. So how much is x explaining the variation in that y variable? All right. We kind of looked at the coefficient of determination when we were looking at ANOVA. All right. Our coefficient of determination is r squared. When you look in JASP, it's going to be a capital R squared because JASP is preparing for multiple regression. And multiple regression uses a capital R, while simple linear regression, one predictor, uses a lowercase r. So if I know the correlation coefficient between those two variables, I can just raise it to the second power or multiply that correlation coefficient by itself, and I get my coefficient of determination. In JASP, the coefficient of determination is given in the model summary table, and I'll show you that for the example that we just looked at. I'm going to go back to those regression results here. And I said that my results for the regression are in this coefficients table. There's a model summary table, which gives us an R and an R squared. We'll talk about this other adjusted R squared later, and you'll talk about that in your next statistics class. So our correlation coefficient is that same 0.876. If we square that, we get to this R squared here, 0.768. And so we can say that about 76.8% of the total variance in happiness scores can be explained by the number of hours of community service students complete. All right. And that is all of what we want to do so far with linear regression. Let's look at another example. It says a school district representative is participating in a community development project to help the county or help county officials determine if they should provide subsidies for a new grocery store. The district representative must present an analysis that includes info on the amount that people in the region spend per month for grocery items, and info on the relationship between the amount spent for groceries and that actual monthly income. We're going to use JASP to answer this question or the questions that follow. Let's go to JASP and let's look at the data. All right. So these last three columns have the data that we're interested in. We have several households here. There's 40 households. This is like an ID variable here. We have the amount that they spend on groceries, and we have their income. Income is like our X value because the income will probably likely influence the amount that a family spends on groceries, right? So we're going to use income as our X and amount as our Y. And so the first question, or the first couple of questions here. Question 1, does any kind of relationship exist between amount spent on grocery items and monthly income? Well, if we're just looking at the relationship, we can create a scatter plot and see what type of correlation, especially if it's linear. Question 2, it says determine the correlation coefficient. And then once we know the correlation coefficient, we can talk about the percent of variation in the amount spent for grocery items, what proportion is accounted for by monthly income. So that's the coefficient of determination, square the correlation coefficient. And so I'm going to start by creating a scatter plot. I'm going to go to descriptive statistics. I want my income on the x-axis, my amount on the y-axis. I'm going to go to customizable plots. I'm going to go to scatter plot. I don't want these graphs. I don't want my regression line. I get this value here. Income is on the horizontal axis. I can't see these labels, so I'm going to widen this. Okay, notice here, 4e plus 3, 5e plus 3, right? This is scientific notation. This is saying 4 times 10 to the third power, 5 times 10 to the third power, 6 times 10 to the third power. 10 to the third power is 1,000. So this axis is 4,000, 5,000, 6,000, 7,000. It's counting by 1,000. But this is my scatter plot, and that scatter plot clearly shows that there's a strong positive correlation, linear relationship between those variables. So there's a strong positive correlation. If we wanted to find the actual value of the correlation coefficient, which that was question 2, I'm going to go to my regression menu now, go to correlation. Doesn't matter which order I put these. I want, excuse me, to display this pairwise. And so I get my correlation coefficient. And with that, I know that it is significant. It doesn't say that I wanted to see if there's a positive or a negative relationship. I'm just trying to see what type of relationship it is. If you wanted to get the confidence interval, you can click on this and you can change your confidence level, right? So I know that this is a strong positive linear relationship, but I know even in my population, I expect a strong positive linear relationship, and this is significant, right? And so that's all the information I need to give me my actual to answer those three questions there, right? So we can say yes, the scatter plot shows a positive linear trend. We can say that our correlation coefficient is 0.945. It didn't ask for us to do the hypothesis test, but that correlation analysis, we saw a significant p-value. That means that there is a strong positive linear relationship that is significant. And since we know this correlation coefficient, um, I know that if I raise it to the second power, to the second exponent, I'll get my coefficient of determination, which answers question 3. So we can say that 89.3% of the total variation in the amount spent on groceries is explained by the monthly income. Now let's answer some additional questions. Question 4, find the regression equation for using monthly income to predict the amount spent on groceries. And then we're going to test the significance of the slope using a 0.05 significance level. So that regression stuff is going to come from the regression menu in linear regression here. My dependent variable, that's our y, that's the amount of groceries. And then my income is my covariate, that is my x. It always goes in the covariate. I'm going to choose backward here. We'll talk about what that truly means in our next lecture video. But these are the coefficients for our study. And then also in this model summary table here, we also see our R squared value is that same 0.893 that we calculated already. But our intercept is a negative value, it's negative 74.367. And our income has a value, our slope is on the row that says income is 0.134. These are the results of that significance test. I also wanted to let you know here, this is probably one of the reasons why we don't always focus on the intercept. Sometimes the intercepts don't have meaning in real life. For instance, here I get a negative intercept. The intercept is the value of y when x equals 0. That means when your monthly income is 0, this is what we expect the amount spent on groceries is, negative $74.367. That doesn't make sense because we're not going to have negative money, and people are still going to, even if you don't have an income, you'll probably still spend money on groceries, right? So it doesn't make sense to interpret your intercept always. And that's why we kind of focus our correlation analysis, our regression analysis on the slopes, because these are the things that are driving the relationships that we're usually studying in research. All right. But we can use this to create our regression equation, and then we'll use this significant p-value here to interpret whether we would reject the null hypothesis for hypothesis test about the slope. And so I'm going to go back to our notes and summarize that information. When we're finding the regression equation, our slope will be multiplied by x. So we have 0.134 times x, and then minus 74.367. I will say that some of you may prefer to write your regression equation in the a plus bx form. You can also write it this way here. Equals negative 74.367 plus 0.134 times x. Either of those ways work. You can say y equals this thing here, or you can say y equals this thing here. It's the exact same thing. The only difference is that when we went over the regression equation, the second method sort of aligns with the a plus bx. So putting the intercept first and then the slope times x second. All right. So if you wanted to write it the second way, I'll just go ahead and put that in the notes that way. that will be fine. But the order doesn't matter. It's the same exact equation. All right. You can also write it using the terms, right? So we have the amount spent on groceries equals that same equation. And instead of writing X, I put the monthly income. And so if you wanted to change the order, once again, you definitely can. Um, to some people, this gets to be confusing, and so I don't want to be very, very confusing, and so I'm trying to stay consistent here. So sorry about that. Question 5, we're going to test the significance. We already saw in the output that our p-value was less than 0.001. Our significance level was 0.05, so we know that we would reject the null hypothesis and conclude that we have significant evidence that our population slope will be significantly different than 0. So that basically just means that monthly income is a significant predictor of the amount that a family spends on groceries. All right, this video has gotten very, very long. Sorry about the changes that I made throughout the video, but I do make mistakes, and I'm glad that I was able to do that in real time so that you can see some of those changes and potentially why I made those changes. All right. But this is it for this video. This was focusing on simple linear regression. What we're going to do next is we're going to go to multiple linear regression where we add more predictors. So instead of having one X value, we may have more than one. All right, see you during our next video.